All right, day 9. Here we go. Okay, so we're in the caves, and they are lava tubes. Cool. Oh my goodness. Oh no, we're gonna need to model how the smoke flows through the caves. Okay, we have a height map. Our goal is to find the low points, locations that are lower than any of the adjacent locations. Okay, we can do that. Most locations have 4 adjacent locations. 4 low points. Right. The risk level of a low point is 1 plus its height. Okay. So we need to find points that are lower than any of the adjacent points. Okay. Okay. We can do this. So let's have a way to index into this. And we'll have that be like x and y. X, y. Our input is going to be, let's make sure. So it's just like a grid of, yeah. Okay. And then what we need to do to parse, we're going to take each line, and for each line, we're going to map read that. So that's just it's basically getting characters, and then we're going to wrap those into a list to make it a string again, a string of just one character, and read that into an int. So I think that should work. Let's just test. Let's do test. Test. And we have a list 2199. Yes, okay. So that's fine. Okay. So let's find a way to index into this input. So height at, and it's going to take a, yeah, I guess we can take input first, and then we can kind of right, input at y, input at x. Yeah, I think that's okay. Let's just make sure that that gets us what we're expecting. So input height at input. So 0, 0 should be 2. 0, 2 is 9. 3, 4, 5, 6. It's too many. Oh. Is this the... I guess it doesn't really matter for x and y, but it might matter for the second part, so I should probably I should probably know what I'm doing. But that was right, actually. 5, 4 is that last 9. And then if we go over, like 1, 0 should be 1. Yes. Okay. So that's fine. So now let's see if we can get let's do like a get neighbors. Input position. Oops. And it's four neighbors, 4 adjacent locations. Yes. So that should be right. And then I think we should be able to filter neighbors that are in bounds. Sure. We can bounds input x, y. Yeah, length. Let's call this width. Yes, and let's call this height. Length input. Okay. So now what we need to do is, let's actually get a way to get this width height. Get size input int. Width height. Width and height. And then in this one, we'll just do width height is get size of input. Perfect. Okay, so far so good. So let's think about how we would solve this. So input. So let's let width height get size input. And then options is going to be yeah, that. And then we need to, so for each of the options, let's see, what are we going to do with the options? At each option, we need to is low point map filter is low point options in sum of 1 plus of map add 1 get height. Is that right? What is that called? Height at. And why is that wrong? Because we need to height at input. Yes, and then let's that's fine. Oh, I don't like having height. I think we should call this depth at. And then we won't be so confused about that. Maybe that's relevant. And then we need to define this. So let's see if it can low point has a lower value, lower depth than any of its neighbors. Come on, Copilot. All okay. So get neighbors, but we also need to filter those that are inbounds, which means is low point needs to take the bounds. We need to like pass the bounds into this, which is a little annoying. So let's actually do that in, let's do that with a where, so we can have that bound inside here. Is low point xy equal let neighbors get filter. Yes. Yes. Bounds input. Let's do it like that. And then let's also do that for depth at. Depth at. So we can just write that like that. And then I like using suck instead of the 1 plus. And then I think I actually want to pull these into that where also, because it feels kind of bad to have a where and a let in this. So let's call this options. Some map. Is low point. So that will give us all the neighbors that are in bounds. And then we need in all have to be What does all take? These all and like any functions always kind of mess me up a little bit. Um, let's just do it with and. Um, ah, let's also get the depth at point. Yes. Map depth at neighbors. All. Okay, and then we want all less than depth at point. And I don't need the map. Perfect. Okay. I feel like this might be right, but I have absolutely no idea if I did it right. So let me just make sure we have the 4 low points. So we're filtering the options to just get the ones that are low points. Yes. Mm-hmm. And then the risk level is going to be its depth, and then we're going to add 1. And so we want to sum them all, and we should get 15. No. Most. Okay, so that was wrong. Why was that wrong? Let's see if we can just get the depth at each of the low points. Well, you know what? Let's start by just printing all of the points that are low points. So it'll be a list of these. So let's try that. So 0, 2. Oh, I'm finding high points, I think. Right? Yeah. Is that gonna be right? Oops, save this. Yeah, that looks right. So let's just undo whatever we just did. And flip this. Oh no, I need the suck back. 15? Yes. So let's get our full input. And hopefully this isn't too much that this will take forever. I hope this actually works. Let's try it. Oh, that was fast. Awesome. Yes, that's right. Okay, I think we can do part 2 today. Let's find out. I shouldn't speak so soon. Let's see. A basin is all locations that eventually flow downward to a single low point. Therefore, every low point has a basin. Okay. Okay. Although some basins are very small. Locations of height 9 do not count as being in any basin. And all other locations are part of exactly one basin. Oh gosh. Find the 3 largest basins. Okay. So let's see if we can sketch out how we want to do this. So I think we should start at the low points again. Because each low point is a unique basin. So if we start at a low point and we recursion it until we have the basin, then we should get all the basins and all of them once each. So let's sketch out what we're going to do. 1, get all of the lowest points. Expand the lowest. Expand each of those points to find to that point's basin. And then take the largest 3 basins, where the size of a basin. I'm just kind of like hoping that Copilot will like know how to do this. The size of basin is the number of locations within the basin, including the low point. And then we need to, what's our result? Or just 3. Multiply the sizes of the 3 basins. Okay, and whoops, do it. Okay, well, that was not the right answer, but it was a good attempt. So it's doing something. Let's do this. Let's do this in the where way again. So let's say we have a basin. So a basin is going to be a list of points, I think. Position. So basins. So let's call that basins. We want the largest 3. Don't we have like a sort by? Sort by. Sort with. Is this something useful? Yes. Sort with length basins. So it's going to be take 3. Oh, you know what? No, we just need the sizes. So it's map length basins. Sort. We want the last 3 though. Okay, so reverse. That's feels bad. And then product, right? Sort map length basins. Yes. And basins yeah, I think this is right. So it's doing the same work as in solve A, and we could probably should just write that out. But this is going to be right. Why can't I do sort? Oh, I need to add sort from data.list. Okay, so we just need to teach it how to expand a basin. Oh. Okay. Yes. So let's let's teach it how to expand a basin. A basin is the list of unique positions that flow downward to a single lowest point. Locations of height 9 are not in basin. Is that enough? Does it know how to do it yet? Actually, that looks like convincing. Input. Expand basin. Should take a list of basins. Basins. Put, sure, whatever. Okay, this isn't quite right though. Inbounds. Right, because we don't need that. Don't need that. This feels good. Filter inbounds, get neighbors. This feels good except for the part where I think this will run forever because it doesn't really seem to be checking. Yeah, okay. This isn't very good. But it might be a place to start. Mm, this shouldn't be. This shouldn't be a list. Right? Shouldn't that be our work so far? Yeah, it should. Not X, but it could be pause. Let's see. Pause. Ah, and that was right. No, but we do need the input. The, this is not right though because it's going to filter inbounds. I want to use like a set. Do I want to use a set? I'm not sure I want to use a set. Um, are basins always bounded by nines? It seems like yes. So let's see, full. Can I wrap? I can't. It won't like. It won't. Oh, there we go. Oh, that's cool. It's really hard to see, but it does seem very clear that there are. Um, the basins are completely surrounded by nines. So is the list of adjacent locations that are not 9. Oh, this isn't gonna. Okay, I guess we have some. We're kind of given some. I think we can assume that each one of these basins actually does slow down to a single point. So I think that's a safe assumption to make. So basically, we just want to like flood fill and stop at nines. Starting at a point, single point, flood fill the basin, stopping at edges, stopping at points where the depth is equal to 9. Well, it actually all type checked this time, so that's a little bit better, but let's see. So we're getting all the neighbors. We have the depth at the point. If the depth at the point is 9, then it's just basin. Otherwise, we're expanding the basin with xy basin. Input head neighbors. I think I want to say this is fine, but we need to check that the point that we're at isn't already in the basin. Already in basin. I don't like doing that filter twice, but let's define that. I guess we're gonna do another where. Where you want me to write that? Not LM. Okay. Sure. Is that right? Well, is could this possibly be right? Let's try this. AOC debug test. Expand basin. Input 0, 0. 0, 0. This doesn't seem right. Neighbors. We're not actually using all the neighbors. Yeah. So what we need to do is we need to like fold over the neighbors. Yes. How do we do that? Else. Fold L. Fold L. Expand to point neighbors. And what does this need to be? Position neighbors basin. Is fold L even what I want? Fold L takes A, B to A to B, and then we need to give it a, yes, this is what we want. But we need to give it a, let's call this pause. In fact, we don't even need XY. Pause basin. And so this takes a basin and a position, another basin, and I want this inside that where. Expand to point. Basin pause equals basin yeah, right? Is that right? That can't be right. Well, that's not right. But it does have all the right numbers in it, it seems like. Basin pause. Enter. Expand basin. I don't like new pause. Right, because it's going to be okay. So let's not already in basin. Map. Why is that wrong? Map. Oh, filter. Yep, and you want me to write it like that. Is that right? No. It is spectacularly not right. Because expand to point. This approach is not going well. So I think what we should do is we should have a list of candidates that we need to look at. Yeah. Let's start this over. Because this isn't going well. Let candidates equal... I think we should do a set. I think we're going to do a set. Set. Did we get it? No. Data.set as set. Okay, we don't need to do that. And we're not splitting at all, in fact. Did we end up using any of these? Sort by. No. Oops. Okay. Let candidates set.empty. And that's going to be a set of position. And then, so basically we're going to have, let's see. So we'll have our state. We're doing like a state machine sort of thing because Haskell. So state is going to be a candidates in basin, points in basin, points explored but not in basin. Yeah. Yeah. And then what we need to, so what we're going to do, expand basin is going to be go set.empty. Yeah. No, set.from list position. Yes, so I think that looks good. And we need to define go, which just takes a let's type this. Type state. It's a set of position. Yes, okay. So this is going to take a set.empty and we're going to have where go. We'll take a state and eventually return a basin. Go candidates points in basin point explored stuff not in case basin. Okay, so if so let's do guards because if we're out of candidates, set.null candidates equals to list points in basin. Otherwise, okay, we're going to need to get the new candidates. So we need to set.pop. Can we like pop an item out of the stack? How would we do that? Let's see. Set set a set a. Oh, I just want to get something out of a set. A find min is there anything like in, God. I guess we can do find min. Wait, we have delete find min. So let new candidates, no, let candidate, new candidates equal delete find min candidates. Does that let me write it like that? The new points to explore. Oh, you know what? First, we should get the we should check if the depth at the current point is 9. So depth at input. Oh, we need to pull out a candidate. So that's let's do this with where then. Equals if depth at candidate is 9, then no. Then we just we pop that and we continue exploring. Then we need to do go new candidates, points in base in, set dot add, set dot insert, candidate points explored but not in basin. Yes. Otherwise, yeah, updated candidates with neighbors. Set insert candidate, points in basin. Yeah. Okay, so candidates with neighbors. No, we're not gonna do it like that. Depth out input. So we only need to define candidates with neighbors, which is just going to be a set of positions, and it's going to be this set of new candidates, but we're going to also, we're going to union. Okay, we can do this. New potential candidates, set dot from list, get neighbors candidate, and we also need inbounds, filter inbounds. And we'll do the same thing we did before, where inbounds input. So this is a set, and then our candidates with neighbors. Yes. Yeah. So let's do this a different way. So we'll do new potential candidates, and then we need to subtract the points that have been explored. So difference takes a set and then another set, and it subtracts. And we need and from data.function. Yes. But I think this should be the other way around, because it should be this minus that. So we'll write like this, even though that's kind of silly. And then we want to add that to that. So that and that. So it's going to be this minus that, and then we add that into the candidates. Does this work? Let's find out. Oh, ooh, I don't know about that. I don't think so. Why not? Why? Why not? Um, I don't know. So we have our candidates. These are places that we need to check. We have our points that are... because we also need to exclude, okay, ones we've already looked at. And that, and points explored. No, what did we call that? Points in basin. Oh no. Oh, what if we did a difference instead? I don't feel good about that. Nope. Because this should be new candidates. There it is. That's our basin. Oh my gosh. Is that it? Does that work? Solve B. Do we have an input? 1134. Is that right? That is right. Oh my gosh. Run B. Hey! All right. Wow. So we actually managed to do that. I'm just gonna clean up a little bit. Well, that's pretty cool. I feel pretty good about that. I'm trying to think. I'm not sure if I've ever like successfully pulled off this sort of like flood fill type of thing in Haskell. I'm sure there's like a very fancy, sweet, like monad way to do it. Um, but I think this worked. I'm sure this is like really inefficient and bad, but that's the name of the game. So it ran. Um, I guess we like it feels like we should like half of this is the same, just like finding the low points. So there's probably a better way to do that, but that's okay. Get neighbors, get size and bounds. I think we did it. I think I'm gonna call that a success today. Certainly went smoother than yesterday, but feels pretty good. So so it's all done, and I hope you found this interesting, and I'll see you tomorrow.